Well, hello, atmospheric and space science. It's been a while since I've seen you. Today, we're going to actually do a physical problem where we are going to determine the amount of energy produced during a solar fusion reaction. So on Friday, I had you go through and look at the solar fusion reaction that's currently going on in our sun, also known as the proton-proton chain reaction. Today, we're going to do the triple alpha process, which is what our sun will do when it eventually swells to become a red giant. So on the sheet that I've pushed out in Notebook, number 7 is this problem, and I am going to do this problem with you. So I've written out my reaction and my masses. You will always be given those things. Okay, that's not something that you could know on your own. So my reaction, triple alpha, is in 2 steps. My first step, my helium nucleus reacts with a second helium nucleus to produce beryllium. That's step 1. Step 2, another helium nucleus, which if you remember is what we called an alpha product or an alpha particle. That's why this is called triple alpha, because there's 3 of them. So a third alpha particle reacts with that beryllium to produce carbon-12 and 2 electrons. So we want to determine how much energy is created by this reaction. So I've made up a table. This is the table that you have in your problem sheet. And I'm going to do each step separately. We don't have to if we want just the overall, but since I want to practice it, I'm going to do each individual step. So first thing I'm going to look at is what are my reactants. Here are my 2 reactants. 1 alpha particle, a second alpha particle. Each one has a mass of 6.68 times 10 to the negative 27th. So 6.68 times 10 to the negative 27th kilograms plus another one. I add those 2 together, grab my calculator, 6.68 to the negative 27th plus 6.68 times 10 to the negative 27th, and I get 1.336 times 10 to the negative 26 kilograms. So that's the mass that I'm starting with. I'm now going to compare that to the mass I end with. What I end with is my products. I only have 1 product here, so that's an easy enough mass to figure out. My product mass is 1.330 times 10 to the negative 26 kilograms. So my mass loss is going to be the difference between them. So I'm going to subtract 1.336 times 10 to the negative 26 minus 1.330 times 10 to the negative 26 gives me 0.006 times 10 to the negative 26 kilograms. Or we could write that as 6.0 times 10 to the negative 29th kilograms. Okay? Either one is okay. Your calculator will probably give you the bottom number. I'm now going to find the energy that was created. To find the energy created, I'm going to use Einstein's famous equation, E equals mc squared. C squared is 9.0 times 10 to the 16th. Now that's already squared. You don't need to square that. So I'm going to take and multiply 6 times 10 to the negative 29th times 9 times 10 to the 16th. Hit that into my calculator. And I already looked up the answer. 5.4. I think it's to the negative 12th. All right, I didn't fully look it up. And I do get to the negative 12th. And the unit of energy is the joule. Okay, so that's how much energy is created in just one step of the alpha process. Now, if you look back into your notes from Friday, you'll see that this one step produces more energy than all 3 steps of my proton-proton chain reaction. Okay, so let's do the bottom one together as well. So again, I'm going to look at my reaction. Here are my products, here are my reactants. I've got 1 alpha particle, which is times 10 to the negative 26. And I've got 1 beryllium, 1.330 times 10 to the negative 26. My other one was to the negative 27th, correcting myself. I add those 2 together. And I get 1.998 times 10 to the negative 26 kilograms. So that's the mass of my reactants. I'm now going to look at my products. And I have 2 products. I have carbon 12, which is 1.992 times 10 to the negative 26. And then I have 2 electrons. So I'm going to multiply this value times 2. And that's going to give me 1.822 times 10 to the negative 30th. Now, to be quite honest, that number is so low compared to this one, I don't really need to add them together. But I'm going to do it just so you see that I do have to have my products. So, plus 1.822 times 10 to the negative 30th. 1.992 to the negative 26 plus 1.822 to the negative 30th. And I get 1.9922. So really it didn't change. Oh, I'm sorry. No, that is a 0. Okay. 1.992 times 10 to the negative 26 kilograms. Okay. Now I'm going to subtract. Okay, so 1.998 times 10 to the negative 26 minus 1.992 times 10 to the negative 26 also gives me 0.006 times 10 to the negative 26, which again I can write as 6 times 10 to the negative 29th. I'm going to calculate my energy. 6 times 10 to the negative 29th times 9 to the 16th. Well, that's the exact same calculation I did in my last step. So I know what energy I'm going to produce. 5.4 times 10 to the negative 12 joules. So how much total energy does the triple alpha product process make? Well, that would just be these two added together, which gives me 1.08 times 10 to the negative 11 joules, which is a lot more than we saw our proton-proton chain reaction make. That's why during this stage of the sun's life, it's going to expand outward. The pressure that comes from this reaction far exceeds the gravity, the weight of the sun, and so that's why the sun balloons outward. Okay, so what are you going to do? Well, we did this one, number 7, together. You're going to do number 8, which is the CNO process, which is kind of like the proton-proton chain reaction, but for high mass stars. So that's what the higher mass stars are doing right now. Okay, they're converting helium into carbon and carbon into nitrogen and nitrogen into oxygen. Our sun is too low mass to do that. If you have any questions, please send me an email. Have a great day.